Hi, I'm Sana Nagai, and this is Crash Course AP Physics, and today we're going to talk about what makes this all possible. And no, I'm not talking about the birds and the bees, I'm talking about you and me and how we are all indirectly conversing through this pixelated universe. That's right, vision. Light, cameras, action, just kidding, shadows, and how it all comes together inside the human eye so that we can enjoy endless hours of internet surfing and/or creating YouTube videos with our camera phones, such as Crash Course. Okay, they're not hilarious? Oh, come on, this show was created by dedicated students just trying to snag an A on the phone. So our goal is to understand how common optical instruments work. Today we will investigate a number of optical instruments in which a combination of lenses and mirrors performs a useful function. Now we can divide those instruments into some simplified categories, so let's start with the camera.
Miss Nagai, was the camera used to take this picture of me?
Why yes, me from the past. Literally me from the past.
So let's take a look at how exactly these mechanisms work using a pinhole camera.
Suppose you point your pinhole camera at a brightly lit bouquet of flowers. Light reflects off each individual flower and leaf. If you hold a piece of white paper near a bouquet, some of the reflected light will shine on the paper, but it won't look like anything. That's because light bouncing off a red rose ends up overlapping with the light bouncing off other wavelengths, making a jumble of light. The whole isolates a small part of the light, sorting a single image, only a few of the light rays reflecting off each.
The whole isolates a small part of the light, sorting a single image from the jumble. Only a few of the light rays reflecting off each point are traveling in a direction that will let them pass through the hole. On the other side of the hole, these light rays reveal an image of the bouquet.
A real camera uses the same principle as your pinhole camera, except that a real one does the job better. For a real camera, the lens does the same kind of job as a little hole. It forms a backward, upside-down image. But the lens lets in a lot more light so the film can do its work quickly. And now, a lens that we're all familiar with, the human eye.
Now let's dive into the human eye and the potential errors that can result from a change in the eye lens's flexibility. Every one of us should be familiar with our eyes. You, me, her, him, them, everyone. The human eye belongs to a general group of eyes found in nature called camera-type eyes. Just as a camera lens focuses light onto film, a structure in the eye called the cornea focuses light into a light-sensitive membrane called the retina. In the optical world, we use the term accommodation to describe the process of changing the lens shape as the eye focuses at different distances. When these structures fail to focus and adapt properly, we get vision problems or diseases. The most common problems with vision are hyperopia or farsightedness, myopia or nearsightedness, and presbyopia, otherwise known as age-related farsightedness. Hyperopia comes from the Greek prefix hyper, meaning over, usually implying excess or exaggeration. With this being said, hyperopia occurs when objects appear too far to be seen clearly as a result of the eyeball being too short for the refractive power of the cornea and the lens. On the other hand, we also have myopia, which occurs when the eyeball is too long, relative to the focusing power of the cornea and lens of the eye. This causes light rays to focus at a point in front of the retina, rather than directly on its surface. Thus, we call it nearsightedness. Next, let's take a real-life look at how the corrective lenses or glasses prescribed to us by the eye doctors assist the vision of our corneas and retinas. In order to stimulate normal eyesight you and I experience, for today's experiment we'll be using two convex lenses. So, as we just saw, the lenses that our doctors prescribe us are not prescribed by their focal length, but by their refractive power, which is the inverse of its focal length. The standard unit for lens refractive power, abbreviated as D, is called a diopter. To reiterate, refractive power, P, measured in diopters, is equal to the inverse, or 1 over the focal length, F, in meters.
Now let's take a closer look at some optics, literally a closer look through magnification. As an object is moved closer to the eye, the object's apparent size gets larger. Apparent size refers to the perceived vision of something that the user or person sees. As the object gets closer, the angle it subtends becomes larger. It's important to note that it is indeed possible for objects with different actual sizes to form congruent angles, thus resulting in objects with the same apparent sizes.
Oh, already? Time for the mystery formula day! How do you find the angular magnification of a magnifier? Focal length must be in centimeters, and the angular size when using the magnifier is larger than that without the magnifier by a factor of m. So I'm going to say m equals theta over theta naught, which equals 25 centimeters over focal length. Aw, yeah!
Now we mentioned earlier that it is possible for different sized objects to appear with the same apparent sizes. What, you don't believe me? Let's take a look at how this illusion works. In reality, Alice is actually standing farther away from the camera than Sano. However, the technique of forced perspective manipulates human visual perception through the use of scaled objects and the correlation between them, and the vantage point of the spectator or camera. This technique is oftentimes used in movies and photography.
Miss Chun, what if we actually wanted to magnify images without the optical illusions?
Without the optical illusions, we would use a microscope to enlarge visions. But what is a microscope?
A microscope is used to get higher magnifications than those that you would get from using just a simple magnifier. In order to zoom in and take a closer look at objects in real life, a combination of lenses must be used. That's right, not one lens, but two. When two lenses work in combination, it's important to know that the image from the first lens acts as the object for the second lens. What does that mean, you may ask? A specimen or object to be observed is placed on the stage of the microscope, directly beneath the objective lens, which is a converging lens with a relatively short focal length. Let's zoom into the magnification process for more details. Get it? Zoom in. The object is placed just beyond the focal point so that its distance is just slightly greater than the focal length, f0, of the objective lens. So the objective forms a highly magnified real image of the object at a distance known as the tube length. The magnification of a microscope objective is called its power. No, Eric, not P equals IV, the degree to which an object is magnified. Many microscopes have a set of objectives that can be pivoted into place to change the overall magnification. The microscope magnifies small objects that can be placed near its objective lens, but a telescope is used to magnify distant objects. The microscope and telescope are very similar because both have a two-lens arrangement, but the objective lens has a long focal length instead of a very short focal length, and the object distance, since it is so far away, is considered to be equal to infinity. Because of this, the converging objective lens forms a real image of the distance object at the lens's focal point. The second lens, the eyepiece, is then used as a simple magnifier to enlarge this real image for a final viewing by the eye.
Telescopes allow us to see what appears to be bright yellow-white shining stars. But did you know that stars come in a variety of colors? So in this segment, we will be taking the time to discuss the wonderful colors of the Earth. And to do that, we will be visiting the awesome minds of Isaac Newton and Thomas Young. He found that white light is a mixture of all colors, as part A of this figure shows. However, when an object such as an aperture passes only the rays of a particular color, that color is seen through the second prism. The index of refraction of a transparent material differs slightly for different colors of light. Therefore, different colors of light refract at slightly different angles. A prism does not alter the light or add anything to the light. It just causes the different colors in the white light to move in slightly different trajectories. Thomas Young performed a two-slit interference experiment, which first showed that different colors are associated with light of different wavelengths. This table, Table 19.1, is a summary of the visible spectrum of light. The slight variation of index of refraction with wavelength is known as dispersion. Dispersion waves, noted as N, are higher when the wavelength is shorter, which is why violet light refracts more than red light. Whew! Now that we're done with the hard descriptions, let's move into an area that we're all familiar with, filters. In real life, a filter works as an Instagram filter works. A filter is a piece of colored glass or plastic that acts to remove all wavelengths except a chosen few. For example, green glass is green because it removes any light that is not green. If you were to view a red apple under a green filter, the apple would appear black because the green filter does not allow red light to pass through. Pretty rad, right?
Alright, so we all know that everything has flaws. And like you, lenses are never perfect, suffering from aberrations. Lens aberrations and diffraction set a limit on an optical system's resolution, its ability to make out the fine details of an object. There's spherical aberration, which is the inability of a real lens to focus perfectly, and there's also chromatic aberration, which is an imaging error produced by the refraction of different wavelengths of electromagnetic radiation through slightly different angles. However, the good news is that you can correct these aberrations. So taking in all this information, we come to find that the fundamental fact is that the minimum resolving power of a microscope, and thus the size of the smallest detail observable, is about half the wavelength of light. This is a fundamental limit set by the wave nature of light. Again? Another one? Okay, it's time for our second mystery formula of the day. What is the formula of resolving power, defined as the minimum resolvable distance of a microscope? Okay, resolving power is equal to... Oh man, I don't know!
Resolving power is defined as the smallest resolvable separation between two objects. It is the wavelength of light in vacuum divided by the numerical aperture of the objective lens, where RP is the resolving power, dmin is the smallest resolvable separation between two objects, 0.61 lambda naught is the wavelength of light in vacuum, and NA is the numerical aperture of the objective lens.
And that concludes today's session of Crash Course AP Physics with Elaine, Sano, Alice, and Lily on optical instruments. Thank you all for watching, and we hope you enjoyed this lesson. Please don't forget to subscribe and follow us on Instagram. A special thank you to Mr. Cohn for a phenomenal year. Thank you.